I would like to present here some of our recent results related to the spin chain system having unit cell of different size and different structure. Actually, our study of this spin system is motivated by numerous successful application of Heisenberg's spin Hamiltonian to the study of peculiarities of the magnetic properties of really existing compounds, such as polymeric compounds of transition metals like copper and nickel, a stacked crystal of iron radical salts, and organic polymer compounds with conjugated bond, and so on. Here I presented only 3 samples of such kind of compounds. This is, where is it? This is polymeric compounds of copper, and on the right side of the slide you can see correspondent magnetic sublattices. Here green balls corresponds to copper cation, carrier of spin 1/2. So in the result, for first compounds, we have uniform Heisenberg spin chain. For second one, we have so-called 3-leg spin ladder. And last one corresponds to so-called necklace spin ladder. All of these magnetic sublattices or spin systems have a unit cell with odd number of spins. According to the extended Lipschutz-Matisse theorem, this system should have gapless energy spectrum. Because of this, there is a possibility of the instability of such kind of system against the periodic distortion of the lattices, which if the gain of magnetic energy exceeds the loss of elastic energy. The corresponding distortion leads to oscillation of coupling between unit cells. And parameter data describe this oscillation, and the gain of magnetic energy in this case is proportional to delta to the power alpha, where alpha is called critical exponent. Actually, such kind of formula corresponds to non-analytical behavior of ground state energy of our system as a function of parameter delta or the parameter delta. Outlook of my talk is presented here. Briefly, I can say that we will consider one-dimensional spin system with emphasis to possible spin piles instability, and consider the peculiarity of magnetization profile at low temperature, especially so-called intermediate magnetization plateau. Let's start our consideration from the study of two simple models. First one, where is it? First one is a chain of trimmers, spin trimmers, yes, and second one corresponds to so-called necklace spin ladder. Actually, necklace spin ladder was the simple model of one of the first pure organic ferrimagnets, polybipiridine axial. According to Lipschutz-Matisse theorem, it's another theorem of Lip. Yes, first system has a single ground state if the total number of spins is even, and second one corresponds to has a macroscopic ground state spin, which is proportional to total number of unit cells. In case of weak interaction between unit cells, we can apply perturbative treatment and obtain the following result. In first perturbation order, in G, where G, let's return back, where G is a coupling constant between unit cells. I would like to skip detail of our consideration and focus on the results. In both cases, for first and second model, In both cases, for first and second model, we obtain effective low energy Hamiltonian of the form of uniform spin chain. The difference in the effective coupling constant. Here, here we have positive constant, here we have positive, here negative. So this means we have antiferromagnetic linear spin chain and ferromagnetic linear spin chain. For first model, properties of the first model is well known because it's exactly solvable model, and it's there is spin piles instability for such kind of model with critical exponent 1.45. For second model, we have unique ground state because it's ferromagnetic state with parallel alignments of all spins. So there is no spin piles instability. Our perturbative treatment also can show the existence of two different types of excitation. Lowest excitation is for both systems. First type of excitation corresponds to the effective Hamiltonian and are gapless. Second one corresponds to the excitation inside of unit cell. So this excitation are gapless. It can be easily shown that such kind of structure of energy spectrum leads to the intermediate magnetization plateau. Intermediate plateau in magnetization profile of this system at low temperatures. The question arises, what we will have in the case of intermediate interaction between unit cell, where perturbative treatment is not applicable. We perform corresponding numerical study by means of quantum Monte Carlo method and density matrix renormalization group, DMRG study, and obtain such a result. For first model, we have intermediate magnetization plateau, which decrease in size, where coupling between unit cell is grows. And you can see here, if coupling constant equals 1, so we have, in this case, we have linear uniform spin chain and no magnetization plateau. It's disappear here in this point. All calculations are performed in units of G0, describing interaction inside of unit cell. Here, the magnetization plateau survive at any value of coupling between unit cells. This means that we have no gapless energy, gapless excitation, which increase total spin bigger than ground state spin for this system, because it has macroscopic value L over 2, where L is total number of unit cells. Let's move to a bit more interesting case of the system which have composed unit cell formed by structural units, for example, 3 side segments and isolated spin, or 3 side segments with different orientation along the chain, parallel and perpendicular. In this case, unit cell has even number of spins. But in the case of weak interaction between structural units, perturbative treatment gives the same results with different coupling constant. A uniform Heisenberg spin chain with non-critical properties. This means that we obtain gapless energy spectrum for the system with even number of spins. In this case, Lipschutz theorem does not work, and usually such kind of system has gapped character of energy spectrum, like well-known Demirel spin chain or two-leg spin ladder. So it's interesting result and a bit unusual result of our consideration. For intermediate value of coupling between structural units, we performed necessary calculation by finite DMRG scheme and obtained that gapless character of energy spectrum survive at any value of coupling between structural units. It is of interest to compare critical exponent for the ground state energy at arbitrary value of coupling between structural units and unit cell for model of trimers with 3-side unit cell and angular model with 6-side unit cells. Yes? You can see at small value of G, we have almost coincident exponent, value of critical exponents, which coincide with our perturbative treatment considered before. And the increase of interaction between unit cell and structural units leads to the change, or leads to increase of difference between corresponding critical exponents. But the more interesting difference between two systems is the dimerization change of size of unit cell during the spin piles transition. You can see first model, yes, because of spin pile transition, has obtained unit cell with 6 spins, so it's so-called dimerization of spin chain. For second model, we have no change in size of unit cell, so it's some kind of unusual spin piles instability, which is published in our paper recently, this year. Okay, what about intermediate magnetization plateau for line and angular model having even number of spins? First model with 4 spin per unit cell behave like set of trimmers, and I think there is nothing to tell more. But second model, angular model, have magnetization plateau which is survived with the increase of coupling between unit cells. Moreover, at a relatively big coupling, we obtain second magnetization plateau. So the system has 2 magnetization plateau for strong coupling between structural units. In order to study the features of this, the corresponding states which are related to magnetization plateau, we perform necessary calculation, which for lowest energy states we specified value of the projection of total spin moment Z, and found that such results. According to our calculation, results of our calculation, distribution of spin density inside of unit cell. In both cases, for first and second magnetization plateau, we have spin wave structure of unit cell, but with different location of negative spin density here and here. I would like to say that here we have so-called reduced spin densities, which according to Wigner-Eckert theorem from the quantum theory of angular momentum, does not depend on the sign of total spin mz. Now let us move to narrow graphene nano ribbons with periodically embedded heteroatoms. The correspondence structure proposed in our work as a possible ferrimagnetic structure, quasi-one-dimensional ferrimagnets. Here red balls corresponds to heteroatoms of spin s small. We use for our study idealized geometry for which all coupling inside of hexagon are the same for neighbor spins. Therefore, if s equals 0, or if s equals 0, for example, if we substitute carbon nitrogen by nitrogen, we have macroscopic ground state spin. But if s equals 1, it may correspond, for example, copper atom or carbon atom. Therefore, s equals 1/2 corresponds to pristine nanoribbons. And we give the main attention to simplest zigzag graphene nanoribbons, so-called polyethylene chain of hexagon, with some embedded heteroatoms. When we studied corresponding magnetization profile, we obtained intermediate magnetization plateau for s equals 1, 1/2, and 3/2. Here we have only 2 results, 1/2 and 1. Actually, it's non-trivial as a result for pristine nanoribbons like polyacetylene. Because polyacene molecule, you can see here, oh no, sorry. Because polyacene molecule, which is presented here, has no small parameter like weak interaction between unit cell and has single ground state. So the possibility of appearance of intermediate magnetization plateau was unexpected for us. We tried to study energy spectrum of this polyacene system, polymeric system, and obtain the energy gap for such for exact energy spectrum by means of finite DMSG scheme and quantum Monte Carlo. This is a bit not trivial because popular spin wave approximation gives for this system gapless energy spectrum. This means this approximation does not work properly for such kind of strongly correlated electron system. As for magnetization profiles, yes, in order to clarify the reason of the appearance of intermediate magnetization plateau for pure polyacene and two magnetization plateau for polyacene with periodically embedded heteroatoms, we create some low energy effective spin models. I would like to speak the detail of this consideration. It's rather cumbersome talk. Therefore, I would like to emphasize that in the result, on the basis of Schmidt work, and torus consideration of spin-spin correlation for vertical sides of graph of these molecules, we propose such kind of model. This initial derivative of graphene nanoribbon polyacene, we move to the spin ladder model, two-leg spin ladder model with ferromagnetic coupling in legs and a set of isolated two spin segments which corresponds to vertical side of hexagons. Definitely such kind of structure explain the appearance of intermediate magnetization plateau because of gated character of the energy spectrum of isolated pair of spin. But such kind of consideration is valid only for a relatively big spin moment close to magnetization plateau. In order to obtain semi-quantitative explanation of corresponding magnetization dependence of magnetization profiles, we should obtain parameter for all of the interaction of our effective model. We can do it easily by means of comparison of the exact energy of small lattice cluster of initial system and our cluster of our effective model having the same number of spins. In the result, we obtain such kind of magnetization plateau. Black curve corresponds to our simulation with quantum Monte Carlo results for the initial polyacene with embedded heteroatom. Red and green curve corresponds to numerical study of the same magnetization plateau by means of our effective model. You can see rather good coincidence, expecting this region probably. So it's a semi-quantitative study. Finally, let us consider the system formed by three-side unit cells as a structural units. Here I presented for spin system having a different ordering of this structural units. In the limit of weak interaction between structural units, all of the system all of the system can be described by the same effective spin Hamiltonian with non-critical properties, yes. Alpha equals 1.35. So we have universal behavior of non-periodic spin system formed by weakly interacting three spin structural units and with non-properties. What we will have for disordered, so it's some kind of disordered system with universal behavior. What we will have in case of intermediate interaction between structural units. Next slide. Actually, for such, for example, for first model, yes, we have interaction end by end for structural units, and therefore, according to Lipschutz theorem, all of the structure, yes, this arbitrary distribution of vertical and horizontal structural units have single ground state. Yes. But we have some kind of disorder, and usually people study disordered system by such a way. They use fixed topology of our system and random distribution of spin couplings. Yes, we have inverse situation. We have fixed spin coupling value and random topology. Such kind of disorder is called compositional disorder, which was introduced for the theoretical study of disordered alloy many years ago, in the middle of previous century. Another type of compositional disorder, we start from periodic system of such kind of structure. According to Lipschutz theorem, this structure has macroscopic ground state spin, and with probability rho, we shift vertical three-side segment by one spin, down or upstairs. Such kind of disorder is different from previous one. And study both of this disordered system by means of exact generalization study, only study for system having small number of spin up to 24, because we cannot do more. And Monte Carlo simulation with some kind of theorem, self-expectation theorem. And in this we obtain the final results for magnetization profile. For first model, yes, for first kind of disorder. We have decrease of the size of our magnetization plateau, which are bigger than corresponding decrease of magnetization plateau with growth of coupling between structural units for regular system. So disorder leads to more quick destruction of intermediate magnetization plateau. For second model, we have smooth decrease of ground state spin of the model. It is of interest, the similar consideration with what?
2 minutes.
2 minutes, okay. With the increase of probability of shifted states, yes, vertical fragments. This means that we have partial destruction of ferromagnetic ground state. If you consider, if you perform similar consideration, numerical consideration for necklace ladder considered before, we obtain destruction of ferromagnetic state. So we move to single ground state even at small value of rho. This may permit us to hope that we may say some important, we may give some important information to experiment with which chemists which are working in field of design of new ferromagnetic materials for preferable topology of corresponding system, yes, chemical system, chemical compounds, in order to decrease the destruction effect of compositional disorder. That's all. Thank you for attention.